Hello. Today we're going to present our DHT11 temperature and humidity monitoring system. It's our final project for measurement and mechatronics. Let's start with the project overview and objectives. Environmental conditions such as temperature and humidity continuously change and directly affect human comfort, equipment, and performance. An environmental monitoring system. Manual measurement methods are not efficient for continuous monitoring and may lead to inaccurate observation. Therefore, an automated measurement system is needed to measure environmental parameters in real time. The problem definition is the same. The challenge was the same as I mentioned on the previous slide. Environmental factors rapidly affect comfort and equipment performance. And our solution is system that measures temperature in Celsius and relative humidity and then calculates dew point. The selected hardware is DHT11 sensor combined with Arduino Uno microcontroller for reliable, cost-effective, automated environmental monitoring with digital output capabilities. Sensor physics and temperature measurement. DHT11 uses a negative temperature coefficient thermistor where electrical resistance decreases non-linearly as temperature increases. The Steinhart-Hart equation mathematically converts the resistance change to accurate temperature values. The DHT11's internal integrated circuit automatically linearizes and calibrates the raw sensor output, delivering digital readings directly to the Arduino. On the right part of our slide, you can see the equation of Steinhart-Hart. It's a complex model used to describe the resistance of a semiconductor at different temperature. Uh, T is for temperature in Kelvin, R is for resistance in ohms, and A, B, C are Steinhart-Hart coefficients specific to each thermistor. On these graphs, you can see the dependency between resistance and temperature for PTC thermistor and NTC thermistor. For the PTC thermistor, resistance is rising while temperature is rising. And for the NTC thermistor, otherwise, while temperature is rising, resistance is falling. Sensor physics, humidity measurement. DHT11 uses a resistive humidity sensor with a polymer film positioned between two electrodes. As the polymer absorbs moisture from the air, its electrical resistance decreases inversely with humidity levels. This resistance changes is converted to an electrical signal representing relative humidity. The sensor outputs digital data proportionally to relative humidity. Here you can see sensor characteristic and static properties, ideal versus real sensor behavior of DHT11. Ideal behavior is linear, but in the real life we will face noise and small nonlinearity for both temperature and humidity response. The sensitivity, temperature resolution is 1 degree Celsius for precise reading and humidity resolution is 1% relative humidity for accurate moisture detection. Both parameters provide sufficient granularity for environmental monitoring applications. Linearity and hysteresis. Linear output within operating ranges from 0 to 50 degrees temperature and 20 to 90 relative humidity. Minor hysteresis effects due to moisture retention in polymer sensing element, ensuring consistent measurements. The response time and bandwidth. The update rate is 1 to 2 seconds sampling interval suitable for environmental monitoring. Bandwidth optimized for slow changing conditions like room temperature and humidity variation. But this is fast enough for HVAC and climate control applications. Error sources and mitigation. The uncertainty sources for our system is electrical noise, temperature drift, EMI interference, power supply, variation, and sensor self-heating. Mitigation strategies are stable 5-volt output of power supply, proper grounding, short wiring, signal averaging, and digital filtering techniques. System modeling in MATLAB Simulink. Our simulation integrates sensor model, signal conditioning, ADC conversion, and SimScape multi-domain modeling. Step response and noise effects are analyzed to evaluate system behavior. Models compare performance before and after optimization techniques are applied. Here we can see the simulation results before optimization. Before optimization, the simulation reveals significant oscillation and noise in sensor output plots. Temperature and humidity readings exhibit rapid fluctuations that compromise signal reliability. These instabilities stem from unfiltered noise propagation through the system model, demonstrating the need to signal conditioning. Here you can see the screenshot from our MATLAB Simulink that is showing the scope of our system before optimization. The simulation results after optimization. A low-pass filter was introduced to effectively dump oscillations in the sensor output. Filter coefficients were carefully tuned to balance noise reduction with acceptable response time. The sampling rate was adjusted to match DHT11's 1 to 2 seconds update rate, ensuring compatibility and preventing aliasing artifacts. As you can see, our screenshot scope from our screenshot has changed a lot. Design optimization summary. The issues that were identified are signal oscillation and noise amplification causing unstable sensor readings. Rapid fluctuation reduced measurement reliability and made real-time monitoring impractical for accurate environment assessment. And solutions applied is a low-pass filter damping implemented with tuned coefficients, balancing noise reduction and response time. Sampling rate adjusted from DHT11 compatibility. Results are smoother, stable data suitable for monitoring. Hardware system design and components. We have DHT11 sensor that is digital temperature and humidity sensor with integrated sensing elements. It provides a calibrated digital output signal. Operating voltage is from 3 to 5 volt DC. Signal via serial interface for easy microcontroller communication. Arduino Uno Atmega 328P microcontroller board with 14 digital in-out pins. Arduino IDE compatible for easy programming. LED indicators, three-color status indication system, green LED for normal conditions, yellow LED for warning threshold alerts, and red LED for critical temperature humidity levels. Real-time visual feedback for monitoring status. And power supply, USB 5-volt power input to Arduino board. Hardware system design architecture. Here you can see our model and the DHT connects digitally to Arduino Uno input pin 2 for data transmission. Arduino processes raw sensor data and calculates dew point using Magnus formula. LED indicators, green, yellow, and red, are controlled via digital output pins based on temperature thresholds. And USB provides 5-volt distribution to all components. Wiring and signal integration. Proper grounding and shielding techniques minimize electromagnetic interference and noise. Stable 5-volt distribution from USB ensures consistent sensing operation. Short wire lengths reduce noise coupling and signal degradation. Pull-up resistor on data line ensures reliable digital communication. Documented wiring diagram including for reproducibility. Software development and code structure. Sensor reading module interfaces with DHT11 library to acquire temperature and humidity data. Filtering module implements moving average, median filter, and exponential moving average algorithms. Output display module controls LED indicators and manage serial output communication. Programming standards, modular architecture, and well-commented code as it will uh, signal processing techniques. Here you can see our graph and moving average filter. It smooths random noise by averaging consecutive sensor reading over a sliding window. Each output value represents the mean of the last n samples, effectively reducing high-frequency fluctuations while preserving the underlying signal trend. Median and EMA filters. Median filter removes outlier spikes by selecting the middle value from sorted samples. Exponential moving average, low pass filter, applies weighted averaging that balances smoothness with fast response time, ideal for real-time monitoring applications. Raw versus filtered signal comparison. Raw signals exhibit oscillations, random noise spikes, and measurement instability, while filtered signals demonstrate smooth, stable, and reliable output. Unfiltered data shows rapid fluctuations that reduce reliability. Threshold crossing cause erratic system behavior. Signal quality insufficient for stable control decisions. On the other side, filtering signal comparison have moving average removes random noise variation. Median filter eliminates spike artifacts. EMA balances smoothness with response speed. Control logic stability. Without filtering, LED indicators exhibit jittering behavior near threshold boundaries, 28 to 30 degrees. Small noise fluctuation cause rapid on-off switching. Unreliable visual feedback makes condition monitoring difficult. System appears unstable to end users. And with filtering, damping effect prevent rapid LED switching near threshold values. LEDs change state only when mean temperature trends are detected. Stable transitions at 28 and 30 degrees threshold reliable visual feedback for environmental conditions. Data visualization and logging. Serial monitor. Real-time numerical data display showing temperature, humidity, and dew point readings provides time-stamped output for debugging and verification of sensor communication with Arduino. Serial plotter. It is Arduino IDE built-in graphical visualization tool displaying live temperature and humidity trends. It provides immediate visual feedback for signal quality assessment and filter performance evaluation. CSV data logging. Automated recording of measurement data and CSV files for offline analysis enable long-term trend analysis, statistical processing, and integration with external analysis tools. And MATLAB dashboard. Enhanced visualization platform with customizable gauges, charts, and indicators. Supports advanced data processing, real-time monitoring, and professional presentation of measurement results. Our sample data visualization. A serial monitor displays real-time numerical readings of temperature, humidity, and calculated dew point values. Serial plotter provides graphical visualization of sensor data trends over time. Both tools enable immediate observation of system performance and signal quality during operation. But for this table, it is the logs. Put it in the Excel format. And here you can see the serial monitor and serial plotter. The system validation approach. Involves comparing filtered DHT11 sensor readings against the high precision reference thermometer under controlled conditions. Multiple test cycles assess measurement repeatability and long-term stability. Test parameters include ambient temperature range, humidity levels, and sampling duration to ensure comprehensive coverage. We were using the formula you can see on the picture, and then we used an error table, which gave us RMSE value equal 1.29 degrees Celsius. Uh, Uncertainty and repeatability discussions. Static uncertainties, plus minus 2 degrees Celsius temperature or plus minus 5% relative humidity per manufacturer specs. Dynamic uncertainties, response time variation of 1-2 seconds, sampling jitter effects, repeatability confirmed through multiple test cycles, showing consistent filtered output within tolerance bands. Filtering significantly improves measurement reliability by reducing noise-induced variance. Technical specification summary. DHT11 temperature range is from 0 to 50 degrees Celsius. Humidity range is 20 to 90% relative humidity plus minus 5% accuracy. 1 to 2 second response time, digital output. Arduino Uno has at Mega 300 to 8P microcontroller, 5-volt operating voltage, 14 digital pins, 32 kilobyte flash memory, and 16 megahertz clock speed. System performance are MSE 1.29 degrees Celsius, 2-second sampling rate, exponential moving average filter, LED threshold at 28 and 30 degrees. Here are the links to our MATLAB certificates. Thank you for your attention.